Let's see, I'm going to share my screen. We're going to be working, there's a lot of different things in here. Some of them really aren't useful anymore, some of them are. But there's this new file here, run MEWS extreme temperature example version 1-1 that we're going to look at today. And it really is the interface for MEWS at this point. And so we have this ability to go ahead and select any of these cities and to not have to run the MEWS optimization, but rather to only generate files. And so there's this function, just extreme temperature, that's come out of MEWS. MEWS.run, from MEWS.run MEWS import extreme temperature, and that function is pretty much all you ever need to use from MEWS if you're just trying to generate files with the current heat wave capability. And so what happens is you use a file path, and this is why this is getting close to being an application, is because I have made everything external, all input sort of external to MEWS. And so this run dictionary file path is actually just a bunch of information. I'll go ahead and open it up, but you don't really have to look at this information anymore. Let's see, use junk. Examples, and then example data. You have two of these .ditc files. They have just, let's see, you open it with a text processor. They have all the instructions for what to do with MEWS. And I mean, this can get a little complicated if you're needing to do something new with MEWS, but I've already run all of these cities at this point, and every single city has what's called a solution file set as a result. And so if you become an advanced user of MEWS, you probably would want to actually add to this dictionary a new city and a bunch of things to it. And then it has this ability to put in this thing called template ID, which every other city has Chicago as its template, which just means that everything I input here is already applies to the other cities unless I change it. And you can see sometimes I had to change the solve options on Phoenix because it was not converging well. So I did change some things here, but most of the other ones came out pretty nicely. And so this file, you have to make reference to a file like this, and then I created this other one because I needed to make a case that ran much quicker. So this is almost the same file, but it's made to run it. The number of files per solution is just one, and a bunch of other things like the maximum iterations instead of being 30 is just one. So it's not going to actually output a valid solution, but it's going to just enable running in a reasonable time, which a reasonable time actually turns out to be like 20 minutes. And so that's what this rundic file path is a path to one of these files. Here I have it just accessing the only one file dictionary. So let's see if that finished with the spider. Okay. Okay, and so this is where we can just open up that file direct. And if I can just find it. Please do stop me if there are any questions. There's MEWS junk. MEWS. Examples. Okay, so some of the stuff I have in here really doesn't matter. This is just an ability to test the code's speed at different places. I have discovered MEWS is going to get a lot faster in a little bit if I can just vectorize some of its components, but for now it's going to be a little bit slower, but it still effectively does its job. And so with this extreme temperature I'd gone over, you have this path file, and inside this run dictionary file path, and inside that the actual inside this oops my word processor. And so inside this thing, there's also a lot of other paths. So it gives, this is where you indicate, okay, what weather files am I going to be going to? You have this historic solution, which is like the fit to the historic heat wave data. That's a text file. You have your weather files, which you can apply several weather files in a list. This is all just Python syntax for a dictionary. So as long as you keep it valid syntax, it will adjust how MEWS works. You can also just copy and paste the whole thing into a MEWS script, and instead of giving a file path, just having it as a variable, and MEWS will automatically recognize the difference between those. And there's all sorts of other things in here that, but I've configured it to where you really don't have to change this if you just want to generate files for the cities that have been going. But these solution files are referenced in these other files, and everything is already in here with the repository. So if I go into Miami, you can see it has all the data for the norms and daily summaries. And if you go into this results, these are the solution files. So I've actually put these on the repository so that anybody downloading MEWS never has to run a optimization again, because optimization takes a day or two on 60 processors, which is not super heavyweight, but it's not something you want to be constantly doing if you're running on a laptop. And you also, and so these files are a tremendous amount of information that MEWS needs to run its model. There's no need to understand it, but it's all there, and it represents the results of an optimization. And you can see the historical solution is the same thing, but without a shift of the information. All of these have attributes: the year, the climate scenario, and the confidence interval on heat waves. This isn't a confidence interval on the CMIP6 information. It's rather the confidence interval on the IPCC tables for heat waves. And so 95% means you're 95% confident that heat wave frequency, duration, and intensity will not be greater than for 95%. And then you have the lower bound 55% and an average 50%. So if you want the most extreme heat waves, you go to 95%. All of these represent extreme increases. The increase just has a confidence interval on it as well. And so the most important thing here is these .tech files. You don't have to have tech to look at them, but this is where MEWS documents very clearly how good the fits are for this. And the way you read this is a Kolmogorov-Smirnov test statistic. And so the first row, there's 3 cases because MEWS is a stochastic model. And so each of these pairs of rows are just new cases. The first 6 are for, you look at this, are for heat waves, and then the last 6 are for cold snaps. And so the Kolmogorov test statistic is basically just the percent difference in the probability, the maximum probability difference between the model in comparison to the historical data. And so you can see here that for January and February of data, you have a rather large difference, 18, basically a probability of 0.18 maximum difference between the cumulative distribution functions. And so your test statistic is very low. If this is below 0.05, you do not have 95% confidence that the variables are the same, and it's actually have to be rejected. And so you can see these first 3 rows of the p-values, which have to be over 0.05 for 95% confidence. January, March, or January, February, and March fail the Kolmogorov-Smirnov test, whereas April, May, June, July, August, September, October, not November, and December all pass. And so I usually, this really doesn't bother me to see this unless it's like falling in August, which is like your peak heat wave month. And that's, you know, and even if it does fail the test, often if you look at a diagram, it's because there's something like a sharp spike in the historical data that really isn't like something you'd want to fit anyway, but the MEWS will output pictures, which we'll see that once we run this. It'll output pictures of all of this for visual verification. Like, am I pleased enough with how this has fit? Because it's really important to know whether the historic heat wave fits are good, and these tables easily drop into tech documents. So if you're writing a report about MEWS, MEWS outputs this right away, so that you have full statistical ability to say this is how the model performed, rather than it just being like a mystery whether or not you have a good fit to the historical data. So that's really important to know that those already exist for the historical fit that and that you have those test statistics on both temperature and duration. And so that gives you a very good sense of whether or not you received a good fit. There's also this last thing, which is also in the repository, which this is just a polynomial fit to all of the CMIP6 data sets. MEWS will generate this if you're running the full optimization, but it takes a long time to run also. And so I put that, I dropped that in so that you could use, this is required, this file is required if you're trying to only generate files. And so with all that information, you're able to just run a simple. So I'm going to go ahead and take this. See, I'm actually going to go back, check something. Okay, yeah, I reduced it to 1. So we're going to go ahead and run this, and I'm hoping that you guys can run this as well. if you're following, and it will take a while to run. I'm going to see if this can start running. Yeah, okay, so it's not bugging out right away. And that's going to take on my end quite a while, probably about 20 minutes to run. And so I'm going to instead run in about 20, 30 minutes. Mine has been running for longer, but while we're waiting for that to come together, I'll spend a little more time explaining how to use this function that we're running right now. So let's see, I want to share my whole screen. Wait a second, what happened? Want to share screen. Okay. So mine is running, but what we have here, so like I was saying previously, this extreme temperature, this demo right here, run MEWS extreme temperature example, provides all the syntax you need to run MEWS on any of these cities. You never need to change this run dictionary path file unless you're changing between this only one file generation is something you can get rid of. And then if you go to MEWS _run.dict, then it will it'll be the actual generation of files that you want to work with. So the inputs that you really have to change are number CPUs. So I usually run this on like a Linux server, and I'll use 60 processors, which is the maximum I have access to. But you can also just put in a -1, which just says use all of the processors you can except for one. So like my laptop here has 11 processors, so -1 would use 10 processors so that I don't totally saturate the machine. And so you can change that, and then you'd also have to change run parallel to true. So running parallel is great, but especially when I'm running on 60 processors, I find that sometimes it crashes for reasons that have nothing to do with MEWS, just having all these different processors running and other things coordinating it. And so if you're having problems, sometimes it's good to turn off run parallel, but boy, does it take a lot longer to get things done. That's why that you can turn that to true or false. This last one, run dict variable, you don't have to change. It just has to be there because inside the let's see, inside this file is that specific example _dir. That's a MEWS variable name, and if you don't define it here in this variable, then Python won't know what to do with your input file. So you could actually put in something else here, like if you wanted another string variable name of myvar, you could actually put in something else like this. myvar equals Houston. And then in your actual, where is it? Oh, I must have closed it. Then in your actual file here, wherever you have Houston, you could actually put, and then that would come out as Houston. There's absolutely no need to do that here, but and unless you're changing things around, you don't need that. And so really all you need are this skip runs and only generate files. Those are the two that you really need. And we just ran this. And we used this only one file.dict. And so it's actually just generating one file, but there's a bunch of steps before file generation that have to be done, and that's why it takes a little while to happen. But if you have 60 processors, this actually runs pretty quickly, and you generate a bunch of files. Once you start generating files, it just spits them all out. So you'll get several thousand files quickly. And so you have this list of all the cities at work, and for this to avoid running the actual optimization, you have to put something in skip runs, or it has to be an only generate file. So if I were to take Houston out right here, since it's not in only generate files and it's not in skip runs, this script would actually start rerunning the optimization on Houston, which will take a very long time. And actually, maybe something that one of you wants to do someday if you start getting in depth with saying, hey, I didn't like Daniel's fit. I need a better fit here. Let me start changing the number of iterations or the weights on the optimization function. All of those things are documented well in the MEWS code, but it's not straightforward. And so that's how you would end up running the full optimization. For now, the entire list is represented in one or the other here, and I'm only wanting to generate files in for Houston. But if I were to change this to Chicago and delete that, then I would generate files for Houston and Chicago. And so that's just what, you can go ahead and generate files for any of these cities just by putting that in here, or else if you want to skip something, go ahead and put that in there. And that's all you have to do right now to generate all the files you want out of MEWS, as long as this is working on your machine. And I'm in the process of generating 200 files per scenario per year per confidence interval, which comes out to 8,400 files per 8,400 files per city. And I'm going to be working on posting those to the data set so that they are available. But I wanted to have this training to make sure also, like if you're doing a really serious Monte Carlo study, you often might need 1,000 files, or you might want to do a convergence study of some kind. And so I didn't want to have to keep on pushing files across. And so I want to make sure everybody could actually use this this function. So mine is still cranking. And I'm going to do is see what it's actually done. Okay, so right now it is in process of outputting a bunch of information. And I'll go over what this information is, but you have all of these comma separated value files that give you information about what exactly MEWS has done. So if you open one of these, you have actual ways of looking at the histograms for MEWS. And so there's going to be a bunch of plots that come out of MEWS, but this is actual numeric data for those plots. And so it's valuable because it allows you to really create your own plots. If you have a report or something, this will enable you to create custom plots without having to just use the plots that come out of MEWS. And let's see if it's actually put out any plots yet. Oh, I think that I turned plotting off in this file. So yeah, you have. So that's what all the CSV files are for. And I think that's where it's, see, is it 102? 212. Yeah, it's finished. It's got to finish. Oh wait, no, it's got the use results. Okay. So now it has output some resulting files right here, and it's in the process of, oh, okay, so mine did finish this now. That's why, but that's just, this is just a command to go ahead and dump out your results as a pickle. So your results here, you can see if you're running a bunch of files, this results dictionary will actually, so results here for, it actually has a bunch of information in it that you could access if you're continuing in Python and you want to do something else. But mostly what you want to look for is that if any of these actually has something called error exception, the extreme temperature function, if it fails for Houston and then moves on to Chicago, it will it'll just fail in Houston, and instead of just stopping and bugging out, it will keep the exception for why it failed and then move on to Chicago. And so if you find your results are full of exceptions, then you might want to send me a screenshot of all the stuff that went wrong. But that's mostly what the results are good for, is to go ahead and see, hey, it did run, it has these Kolmogorov Smirnov tables and stuff like that it went ahead and wrote out. And everything else is in here also that has to do with the list of files used and so forth. And so it generated a bunch of EPW files here. A much shorter list. It's just 42 rather than 8,400. And you can see that each of these is just R0, meaning that you have just one realization for each of the different scenarios and years that it went through. And so that's what you're able to do is to create files, and you'll always end up, if it ran successfully, you end up with this MEWS EPW _ results, and you'll find all your files here. Now I do find I'm having to restart on my 60 processors. I often start this whole process and it runs successfully for a while and then it fails. And I sort of have to check, like, okay, did it get through to Miami? And oh, there's no MEWS EPW file. Yeah, this just has what's in the repository so that you're able to run and generate new files. And so it's sometimes a little bit of a tedious process, but that really isn't MEWS's fault. It's more of a problem with how parallel running executes, and maybe my Linux server is the main problem. So are there any questions? I mean, that's pretty much the end of my demo. If Al, you're able to get the same result where some files got generated, then it's working. Go to examples. So I'm actually, like, I have Miami, I've completed 8,400 files here. So I have a tremendous number of files for Miami here that I generated, and the results here actually have other things in here, like, so we looked at those tech files, right? So if you're looking at like temperature here, and oh, come on. And you can see Miami has a horrible fit. This should be greater than 0.05, and has a horrible fit right here. And you can say, okay, well, let me look at January's historic fit. So you can see this Miami Airport historic month 1, the durations and the month. And if you open that, sorry, I'm running over a network. You can actually see, well, is it a horrible fit? It's not passing with 95% confidence, but it's actually these spikes here that are probably causing it to not pass. And visually, I think it's actually fairly pleasing. And in fact, towards the end here, it seems pretty right darn on in terms of your maximum temperature for heat waves. So this is the actual historic fit. Some people may only want to look at stuff like this and say, okay, above climate normal average, my extreme heat wave is about 12 degrees Celsius above the average of climate normals. So MEWS is always baselined off of the 1991 to 2020 climate norms, 50% temperature. And so that's what 0 always represents on these. And it says that peak temperature increase from daily climate normals average. And when it says average, it's because it's daily. It's the daily average normal. So you sort of you have to always remember that's what if I'm going to use a plot like that, I have to take the daily average of the 1991 to 2020 climate norms. And then I could say the worst kind of heat wave I've ever seen in Miami is about 12 degrees above that, to 12 degrees Celsius. And so that actually gives you a case for historic heat waves. And then you can also look at the durations. Oh wait, we were wanting to look at month 1. Okay, so month 1, you can see why that test statistic came out so badly. I think the fit's fine, but the historic data has stuff going on. It's not smooth. And so what I've done, I've got a publication right now for Worcester, Massachusetts, and what I do is that I show the tables of statistical fits, and then I review anything that's not meeting 95% confidence and waving my hands and saying, hey guys, it's fitting as good as you would actually want a model to fit. And I've actually seen cases where that's not the case, where there's something going on, like there's a big double humped distribution. I'm like, ah, shoot, MEWS is not going to fit that well. And so it really is up to the user to decide whether they're going to use what MEWS has output. And it is only a model, and a lot of this data, though, there is no more information available anywhere. So it's like, well, you can't get a good statistical fit if you don't really characterize your histogram completely. This is very characteristic of data that has sort of like these blocks of information that means the resolution doesn't meet what you actually need to make a smooth histogram. And so whenever you see something like this, right away, I'm like, this is good enough. It's the best you're going to get out of the historical information. And so then you also have the same thing for all your future shifts, but you have a new aspect to it. So I'm going to go ahead and go to an actual more important month for heat waves. And so if you're not wanting to run a Monte Carlo study, you can always choose one of these PNGs based on climate scenario, confidence interval, year, and open it up and look at how MEWS has shifted your heat wave intervals. Yeah, all of this Miami data is horrible. Like the data itself is not what you'd want it to be. Most of the other ones don't have these jagged pieces in it. So there must be something with how Miami was recording their data, but I still think the data is useful. And so what you see here in this magenta line is the historic 10-year, and then the red line is the historic 50-year intervals. Then these arrows came out wrong. I don't know why it did it that way, but then when this blue dotted line is the future shifted fit for MEWS, and the red dotted line is the future shifted 50-year event for MEWS. And then the dashed blue and dashed red are the historic shifted. And so if you were just wanting to, if you're only wanting to get a maximum heat wave for the future, you don't have to use Monte Carlo study for MEWS. You can actually use just this red dashed line. If you want a 50-year event in 2020, well, 2020 is not that exciting. If you go to 2080, let me open a different one. That's why the arrows are going backwards, is because it's almost no shift. And the reason 2020 is the future is because CMIP 6 is baselined off of 2014. Let's go to 2060. Okay, so here's an example where you actually have a larger shift. And so this shows that, you know, MEWS has shifted the 10 and 50-year events, and then the historic events also shifted. And so you actually get thresholds you could just use for scenario-based analysis, saying, okay, the absolute maximum heat wave, you could use the historic value or the MEWS value. MEWS has this problem that it doesn't have enough to like shrink this. It just moves it, and the analysis often ends up with your 10-year too low and your 50-year too high, but it being right in the middle. This being right in the middle, but it's the best I can get it to fit presently. But either way, you could go ahead and use one of these values as your absolute maximum heat wave shift. And so you can see here, this is in August. We were looking at January where the heat wave shifts were different, but the historic 2014 heat wave, a maximum would be about 7.5. But then you could say, if I'm going to test against SSP 585, 50% confidence interval on my heat wave increase in frequency, duration, and intensity in 2060, I'm going to use a 12.5 degrees Celsius heat wave from my peak temperature increase from daily climate norms average. And so that allows you to create a scenario-based resilience analysis from MEWS's output. And so that's one way MEWS can be used. Or else, if you want to use the EPW files, they reflect the distribution here. Instead of just a threshold, it actually reflects this orange distribution, which has been shifted so that the thresholds are correct. So the fit has emphasized the extreme and not so much this. This is just actually sort of like a kinematic stretching and shifting of the historic distribution, which the cold snaps don't get shifted at all. They just stay at their historic levels. I eventually want to change that if there'd actually be information about what happens to cold snaps. I mean, I might expect cold snaps to shift a little bit to the right, but then lengthen out some on this side. And so there'd be all sorts of games that can be played using the MEWS model, but that's not done in MEWS yet. I sort of need information because there's no information about how winter storms will change, but that's where I want it to go eventually. And so that's what all of these plots are for. And they can also just be used directly. The durations often, I don't shift durations at all. I just allow durations, even though everybody says heat waves are going to be longer. I don't shift it because I didn't have good information about how durations are going to shift. I just have intensity and frequency. What happens is we get 50-year heat waves on the IPCC tables. 50-year heat waves start happening almost yearly, and 10-year heat waves start happening a couple times a year. And so that's how MEWS actually produces that in the EPW files, is that all of a sudden you have these a significant uptick of frequency, and then you have a significant uptick in intensity. But in terms of significant uptick in duration, I don't mess with that because IPCC didn't really have that. But one of the things is if you do take a scenario-based approach, it's very easy to say, okay, so MEWS has given me my maximum temperature threshold on that plot. This is the delta I want to apply. And then I'm going to also apply 2 times the duration. And then you can create a heat wave scenario on your own. That's where it may turn out. I mean, the EPW files are really useful for a resilience Monte Carlo study.
Okay.
But they're just going to have tons and tons of, it's basically, they're just single statistical realizations of these duration histograms and the where's the temperature one, and these temperature histograms. And so what you may need to be doing is just looking at these. You know, you probably don't want to do it visually, but the CSV files that MEWS outputs contain the actual, contains this orange plot and this blue plot. MEWS outputs that. This is just a regurgitation of the historic data. This is the MEWS model fit into the future. Whenever it has a name that just has historic on it, you won't see all of these shifting. You'll just see the historic versus the MEWS fit. And it's a good way to just say, hey, this is what my extreme weather is going to look like. And MEWS sometimes has a tail here. I wouldn't ever use the tail end of this. That's not realistic. But the blue, or else a shifted threshold, is that really is your absolute extreme for 80 years. It's a 80 years of data looking at your extreme cold case. And so these plots and the CSV files that have them are probably your better product to be working with, unless you do want to do the Monte Carlo type study where you're testing the grid over and over against lots of different heat wave and cold snap cases, because This has all the information. It's just a matter of processing it. And you can find all those thresholds by reading this into Python, and then working with it from there. And I realize that like the EPW files are great, but eventually really you would just be reconstructing what's already in the plots. It sounds like you need to get those maximum values out of the historic distributions. So just real quick in terms of like a couple of things about this file that is the file that will actually run all of this. So if you want, let's see, edit. So you can see this plot results is true here and true here for both future and historic. And that's what will output all these PNGs. With this only one file, I went ahead and set it to false because I'm trying to get it to run faster, and outputting those PNG files is, you can see it's false there. Outputting those PNG files is expensive, and it also takes up a lot of disk space. And so that's yeah, you can see other things like test mode is true. So if you use this only one file, it'll output invalid results. You have to use this MEWS run.dict. The only one file is to test really quick whether or not it's working. So any other questions or thoughts? I'm going to go ahead and stop sharing my screen and stop the recording.